Hello everyone! In this video I would like to show you a transience criterion. Let us say that we have xn with n in z plus, a Markov process taking values on a countable space S with transition matrix P. We assume that this process is irreducible. That is, we assume that for every pair of points A and B in S, the state space, there is an m such that the probability of jumping from A to B in m steps is positive. We can also write this in matrix form. P to the power m at the point AB is larger than 0. The theorem says the following. An irreducible Markov chain xn with n and z plus on a countable state space S is transient if and only if there is a function f from S to R plus and a non-empty set A contained in S such that the expected value of f of x m plus 1 minus f of x m, given that xm is equal to x, is less than or equal to 0 for every x outside of A, and there is y outside of A for which f of y is less than the infimum of f of x for all values of x in A. So for the proof, we first consider the only if part of the statement, which is to say that we assume the process is transient and we're trying to find a set A and a function f that satisfies the required properties. So, let tau A be the first time that the process xt visits the set A. Fix x bar in S, and let A be the set composed of the point x bar. Define f of x to be the probability of coming back to A in a finite time given that you start at x. Note that f of x bar is equal to 1, and that for every x different from x bar, the expected value of the increment f of xm plus 1 minus f of xm, given that xm is equal to x, is equal to 0. By transience, there is y in S such that f of y is strictly less than 1, which is the value of f of x bar. Therefore, there is a function f from S to R plus in a non-empty set A, for which the expected value of the increment is less than or equal to 0 for all x outside of set A, and the infimum of the value of the function f outside of set A is less than the infimum of the function f on the set A. So this concludes the proof of the first part of the theorem. And now we move to the if part of the theorem, the converse. So what we want to show is that the process is transient if there is a function f from S to R plus in a non-empty set A such that f is a supermartingale outside of A, and a y outside of A such that f of y is less than the infimum of f of x for all values of x in A. To prove this result, we rely on a key lemma. So the key lemma is the following. Let xn with n in z plus be an fn adapted process with state space on the measurable space sigma e. If there is an f from sigma to R plus that is measurable and a set A that is an element of the sigma algebra E for which the expected value of f of xm plus 1 minus f of xm given that xm is equal to x is less than or equal to 0 for all x that are not in A, then almost surely the probability of coming back to A at a finite time, given the sigma algebra f0, is less than f of x0 divided by the infimum over all x in A of f of x. This function f is useful. We call it a Lyapunov function as it gives us some knowledge about the trajectory of the process. We can read the following quote from the book Non-homegeneous random walks by Serguei Popov, Mikhail Menshikov, and Andrew Wade. A Lyapunov function that is a supermartingale outside of set gives us an upper bound on the probability that the process started outside that set ever reaches its destination. Now we move to the proof of the lemma. Let yn be the function of xn stop at tau a. Note that the condition we have from our hypothesis on f, on the increments of f, translates into the condition that yn plus 1 minus yn given fn is less than or equal to 0. That is, yn is a supermartingale. Now, a positive supermartingale converges almost surely. So by the super-martingale convergence theorem, there is a random variable y infinity such that almost surely yn converges to y infinity. Using the super-martingale property of y, we obtain that y0 is larger than or equal to the lim-inf of the expected value of yn given f0, which by Fatou's lemma is larger than or equal to the expected value of the lim-inf of yn given the sigma algebra f0, which is larger than or equal to y infinity on the event that tau a is less than infinity. Now we note that y infinity on the event that tau a is less than infinity is equal to the value of f on x tau a on the set tau a less than infinity, which is larger than the infimum of f of x on the event tau a less than infinity. Now we repeat what we just saw, and from here we continue to see that f of y0 is larger than or equal to the probability of tau a less than infinity times the infimum of f of x for all x in A. This implies that the probability of tau a being less than infinity is less than f of x0 divided by the infimum of f of x for all x in A. This concludes the proof of the lemma and gives us a proof of the if part of the theorem. Because if we take x0 to be the y that is strictly less than the infimum of f of x over x in A, we have that the probability of tau a being less than infinity starting from y is strictly less than 1. In the next video we'll consider how to quantify recurrence and transience. That's it for now. See you soon and take care. Bye!